All right? What we did last time was to start looking at the transistor stages, and we did a parallel development. So we'll continue that. We'll develop some of the stuff for example, BJT, and then we'll look at the equivalent of them for MOSFET, and we'll have a discussion about how it looks like in the general case for any arbitrary device. But what we will do first today is we're going to spend a little bit of time looking at some of the bipolar stages, just reviewing quickly what the core stages are and how they behave and how do we model them. So one of the things that we looked at last time, the first thing we looked at was really the only amplifying stage we looked at was the common emitter, for example, or common source without source degeneration. So this is the way we show it, again, just to refresh your memory. So this is VCC, this is RC, and this is Vin, and this is Vout. Now, of course, one of the things we saw when we looked at that was that even from a large signal perspective, if you just think about this as a Vin, Vout characteristic, you can draw the Vin, Vout characteristic, and we did derive it. Basically, you can write the output voltage as VCC minus the voltage drop across here. So Vout was VCC minus RC times the current, the collector current, which is related to the base emitter voltage, which is now Vin. So and we know how that dependence works. We know that it's primarily exponential. So it's IS e to Vin minus Vout. Vin, I'm sorry, over Vt, the thermal voltage, Kt over Q. And if you plot that, of course, that's for forward active region. So you start from here, you start from VCC when the Vin is 0. So this is Vin, this is Vout. And you initially started turning the transistor on. The current is small first, it's exponential, but then it grows exponentially. And then, of course, it's not going to go negative because once this voltage gets below a certain level, which is like 0.1, 0.2, this transistor is going to enter saturation, meaning that this junction, the base collector junction, is going to get forward bias, and you get something like that. So that would be the characteristic. And of course, the gain is the slope of this thing, which you can see is negative, and depends on when it happens. You can see this is a very nonlinear behavior, of course, right? And then the other thing that we did, we looked at it from the pi model perspective. We said that generally, pi model is more useful when the emitter or source is grounded or connected to a fixed potential. Now, if generally when collector or source or terminal 1 in the ATD, arbitrary transistor, three-terminal device, is not grounded, you will see that the T model is useful, which is a lot of times. T model works better. Again, you are welcome to use whichever model you feel more comfortable with. This is just a suggestion, not a rule. So you can do it any way you want. If you do it properly, you will get the correct result. But when we did this, so this is from last time, we had the R pi here. And here, of course, the DC part of this thing, the bias part, will disappear. You only are left with the Vin, the lowercase Vin, which is the AC part of it, the perturbation on top of that. So you have a R pi here, which produces a V pi. And then we had the basic pi model. You had the GM, V pi, you had the RO, we had the RO, and then we had the RC. And this was Vout. And why is RC connected to ground here? Because in the large signal model, it's connected to VCC. It's connected to a constant potential, which basically from an AC perspective is 0. So there's no difference between this and that from an AC perspective. They're both constant. The derivative of both is 0. So, okay, so we had this, and then we calculated the gain to be, so AV, we demonstrated the small signal gain to be GM times RC parallel RO. And we saw that if the maximum that you can get from this kind of stage was essentially GMRO, assuming that you present a very large resistance. We said that you can actually, if you could load it, if you had an ideal current source here, it would become an open loop. It will allow you to bias the device, but it will still remain open loop. So what happens is that basically GMRO, so AV max was GMRO, which we basically saw GM being IC over VT and RO being VA over IC, was essentially the ratio of VA over VT. So that was the thing. Now also there's an input and output resistance that's associated with this. So there's, if you look into the input port from an AC, from a perturbation perspective, you see what we call an Rin. And if you look into the output terminal, and you null the independent drives, which is namely this guy, you will see a resistance. And it's clear what Rin is. I mean, this is obvious. By looking at it, you can see what it is. So Rin is really R pi. But if it was not as obvious, how do we generally determine that? We apply a test voltage, let's call it Vx or Ix, and calculate the other one in terms of it. So if you're applying a Vx, you calculate Ix in terms of Vx, and you calculate the ratio of Vx to Ix. And we'll see examples of that going forward. So if it doesn't make immediate sense to you, don't worry about it. But it would be obvious here to apply it. And again, for the R out, the same deal. So we can actually try doing that here just to make sure that you're on the same page. So if you wanted to calculate what R out is, you apply some sort of a Vx, let's say, and then you're trying to calculate Ix. And you have to null the sources. So when you null the sources, where are the independent sources, other independent sources? This guy, right? So you null it, what happens? This becomes ground, becomes shorted to ground. So what is V pi? 0. So what is GMV pi? 0. So what does this current source become? Open. So what are you left with? You're left with these two, right? So you apply Vx. What is the current that will flow? The current that will flow would be Vx over RC parallel RO. And therefore, if I wanted to go through the procedure formally, R out would be ratio of Vx over Ix, which from this calculation you can easily see it's going to be RC parallel RO. Now, we want to also, as we go forward, we want to develop some sort of an intuition about the devices, transistors in general. So for example, if you think about it, and again, this is some sort of a rough way of thinking about things, but it's useful to start thinking about it that way because we'll refer to it. So if you have a transistor, really what these resistors that you're talking about are really Thevenin or Norton equivalents of what is inside everything else. When you look into it, think about this as a black box, right? And say, what is the Thevenin equivalent of this thing? The Thevenin resistance of that thing, how is this calculated? The Thevenin resistance of this entire thing. You null all the independent sources. We nulled this. And you determine what's the resistance that's seen, right? Or the Norton equivalent. That's how we calculate. So it's basically the Thevenin or the Norton equivalent of that box from a network circuit theory perspective. But now in general, if you have a transistor, let's say a BJT, it's good to develop a sense about what are the resistances seen looking into the three terminals of the transistor. Not only what the values are, also kind of like get a feel for how large or how small they are. So let's talk about that briefly. So what is the resistance? And when we say that, we kind of implicitly mean, when we talk about it, really it's the resistance that you see if the other two terminals were AC ground, meaning that the transistor still is biased properly, so it's in the forward active region. You're not short-circuiting everything to ground, really. You're biasing it, but there's no perturbation on it. So from an AC perspective, they're grounded. So if from AC perspective, these two other terminals were grounded in this model, what is the resistance that you see looking into the base to ground? Let me keep my color code consistent going forward. So what is this resistance that you will see looking into the base? What would you see if the other two terminals were AC ground? R pi, right? Because if you're AC ground, this stuff disappears, so what you see is R pi. Now the other thing so now the other question is that what is the resistance you will see into the collector, looking into the collector, when the other two terminals are AC ground? What would you see? Just the collector by itself. And that's shown like this, for example, if I wanted to show it that way in the circuits. And this resistance is the resistance looking shown here, like this. So, yes, but RC is not there. So we said just a transistor, right? Correct. RO in parallel with RC, but there's no RC because we said we have AC ground. It's like connecting it to some supply voltage directly, collector, and looking at that. Or some bias current. It's RO. It's just the RO, right? And what is the resistance you see looking into the emitter? RO parallel to R pi. Is that so? Because there's a current source now. You have to take it into account. And it's actually easier to see it in the T model. So let's go to the T model and see how this thing looks in the T model. Looks like a T model. So you have alpha Rm, you have alpha IE, this is IE, right? And then you have the RO. So this is the emitter, this is the base, and this is the collector, right? So for that, of course, to have meaning, then the emitter is not grounded because you want to look at it. So what do you see? If I ground this terminal and ground this terminal, right? Would the value of that current source matter? I mean, the current source is not zero. The current, if I apply a test voltage, let's say a test voltage of Vx, Vx applied here, well, this is bad drawing. Okay, Vx is applied here. It would induce some IE, right? Which induces a current source here, a current through the current source. But this current source is shorted across because it's shorted on both ends. So that current will flow inside that loop, so it wouldn't affect anything else, right? It's a shorted current source, or the current will go through the loop, the closed loop here. So fine. So that doesn't matter. So what else do you see? You see two resistors in parallel, alpha Rm in parallel with RO, right? So what you see here is alpha Rm parallel with RO. But should I really worry about RO when I'm talking about Rm? Let's think about the values, right? What is Rm, let's say for 1 milliamp? 1 over GM. Yes, which is basically at 1 milliamp is IC over VT. So it's like 1 milliamp divided by 25 millivolts is 40 millisiemens. It's GM, so it's 25 ohms at 1 milliamp. And it scales. The smaller the current, the larger the Rm. Right? So this is like so R pi, by the way, what's R pi? R pi was beta Rm, right? So let's say beta of 100 for the sake of argument. So you're looking at 2.5 kilo ohms. So this is in kilo ohms, right? 1 kilo ohm, 2 kilo ohms. If the current is smaller, like 10 kilo ohms, things like that. So Rm is in tens of ohms. Let's say for 1 milliamp, this is 25 ohms. This is 2.5 kilo ohms. And RO, what is RO? Let's say a VA of 100. So it's 100 divided by 1 milliamp, it's 100 kilo ohm. So these three, you can see they're on very different orders of magnitude. So this is on tens for 1 milliamp, or milliamps of current. This is on the tens of ohms. This is on kilo ohms. And this is in hundreds of kilo ohms. So each one of them is about 2 orders of magnitude different from. So this is 2 orders of magnitude higher than that. This is 2 orders of magnitude higher than that, roughly. So this is 4 orders of magnitude higher than that. So it's really ridiculous for me to say it's alpha Rm parallel with RO. Because it's alpha Rm. That's one thing that's, one of them is 4 orders of magnitude higher than the other one. So this is alpha Rm. A lot of times we just say Rm. But these are good things to remember, kind of think that for a transistor, looking into the emitter, you see roughly alpha Rm or Rm. Looking into the base, you see R pi. And looking into the collector, you see RO. So you can see that we have 3 terminals from very low impedance to mid-level impedance to high impedance terminal. And this is important when you design circuits because there are places where you need low impedance and there are places where you need high impedances. And that would affect the way you use the transistor, the topology of the design. Is really dictated by these impedance levels, primarily, really. So that mindset should be on the back of our head as we go forward. So we did this. By the way, let's see if we can get to the same. You can say, well, this model looks kind of bizarre. This is very obvious that I can calculate the input resistance to be R pi here, but it's not clear that it's R pi here. Well, let's see if it's R pi here or not, for the sake of argument. So let's say you have something like this. And then you're trying to calculate what the input resistance is, Rin. You can apply a Vx and measure Ix, right? When you apply Vx, so if this voltage is Vx, what is this current, IE? That's the key current, right? What is it? You have a voltage Vx across a resistor alpha Rm. What is this current? Vx divided by alpha Rm. So IE is Vx divided by alpha Rm. Right? Now, if that's Vx over R, so what is Ix? What is this current? in terms of IE. This current is IE, this current is alpha IE. So this current is going to be 1 minus alpha IE. So IX, which is 1 minus alpha IE, and IE was Vx, so it's 1 minus alpha, Vx over alpha Rm. Now this quantity has a name, alpha over 1 minus alpha. It's beta, right? So this is really 1 over beta, so this becomes Vx over beta Rm. So if you look at Rn, which is going to be defined as Vx over Ix, you can easily see it's beta Rm, which is R pi. So obviously it should give you the same result because it's an equivalent model. Now, you will see that how we use these things as we go forward, and you can see that this can come in handy. This was a case where it's not particularly useful because the emitter was grounded. And then we'll next see how it's useful when the emitter is not grounded. So this is kind of like what we call the basic emitter, common emitter, without degeneration. So, but what is the problem with this kind of stage? If you look at the large signal behavior of it, there's a little problem. I mean, depending on what you're trying to do with it. If you're trying to use it as an amplifier, let's say to amplify audio. Let's say you want to take this and you attach it to a microphone and amplify the voice. Would this be, what would it do to the audio the way it is? Well, it provides gain, but it's very nonlinear, right? It's an exponential. And exponentials are particularly not particularly linear. So what can we do to linearize it? Part of the reason it's not, so why is it so nonlinear? Let's think about this. Why is it so steep? I mean, it's a good thing that it's a steep thing in a way because it gives you a lot of gain. But it is challenging because now it has a narrow range of operation, and in that range of operation it's quite nonlinear. So why is it that? Where is this nonlinearity coming from? It's coming from this exponential, right? Which is coming from the transistor, which is coming from the Boltzmann distribution, which is coming from the Fermi-Dirac distribution, from, well, so on and so forth, right? So it's this exponential. Now, why do you see this exponential in its raw, fully exposed form? Because you're applying your input directly, all of it between the base and the emitter, right? So all of it is applied directly there. So every fluctuation that you have goes directly through the exponential. So one of the things that you can do is to create a situation where this voltage is actually divided between that and something else. So one of the ways of doing that and a reasonably good way of doing that is to introduce a resistance in the emitter. Now, once you have a resistance in the emitter, or in the source later on, as we'll see, or in terminal 1, so you introduce a second resistor, RE. So this is common emitter with emitter degeneration. That's what we call this. So this is still V in, and this is V out. Now you have a resistor here. So what happens is that when you apply a voltage V in here, it drops across the VBE here, which in the small signal appears like alpha Rm, and RE. Right? So there's a voltage divider. This is a linear resistor, and this is a nonlinear resistor, really, which in the small signal model becomes linearized. So what do we get for gain and other properties of a stage like this? What is the gain of this stage? So how do we find out what the gain of this stage is? Let's go talk about that. So we can think about the small signal model. So as our kind of like, I guess, our rule of thumb suggests that since the emitter is not connected to ground, let's use the T model. So you have alpha Rm and Re. And for now, let's ignore the Ro for a second. And then we'll come back to it. So we have the Rc here that goes to where? To ground. So this is V out, lowercase, V in, small signal, small signal. And this is IE, and this is alpha IE. So in this picture, what is the thing that determines V out? It's that current source, right? That dependent current source. It's pulled out of Vout, out of RC, sorry, to produce Vout. So we know Vout is going to be what? This current source, negative alpha IE times RC. And why negative? Because it's being pulled out of it as opposed to being injected into it. So it's just a polarity question. So the question is, what is IE? What is IE in terms of Vn? Well, it's a pretty straightforward thing. You know this voltage is Vn. There are two resistors here, right? So it's this voltage divided by these two resistors. So IE is simply Vn divided by alpha Rm plus Re. And if you plug that back into that guy, you will get Vout in terms of Vn. So if you do that, you see Vout over Vn is negative alpha Rc over alpha Rm plus Re. And so let's see if this does reduce to the gain we calculated before, the GMRO. Okay? Does it? If Re is 0, this stage reduces to the previous stage. It becomes non-degenerate, right? So if you set Re to 0, the alphas cancel. You have Rc over Rm, or GMRC, negative GMRC. So it reduces to that, because we've ignored RO already. So yeah, fine. It's an equation, right? Is there a better way to think about this? Yes, there is a better way to think about this. This is actually a pretty decent way to look at it, better than a pi model, I think, because what you see is basically you see the transistor. This is the transistor. This is where you have the potential you've lured, and this is the current that gets injected into the collector. The electrons that get injected into the collector, or if it's a PMP, the holes that get injected into the collector. So, but there's still a simpler way to think about this. If I tell you what is the gain of this thing, if I show you a stage and I ask you for the gain, and you've done a little problem already on this, so you should have developed a little bit of a intuition on this. So here's the thing. We need to really, if you're designing, we will be talking about this like 10-second design exercises. So what I wanted to be able to do, you to do and us to do, is that if we have a stage and we say we want to kind of come up with values that make it have, let's say, make it stage that has a gain of 5, right? You should be within 5 seconds come up with something that's within 10-20%. 10 seconds you should come up with something that's within 10-20% of something that gives you a gain of 5. So if you give me a gain of 4.7, 4.8, I'm okay. If you give me something that has a gain of 4.5 or 5.5, it's okay. If you give me something that has a gain of 50 or a gain of 0.5, then we are not okay. So we are going to be building towards that. So for that, we need to really understand what's happening. What's really happening? In this transistor, you have a current here, and you have alpha times that current. If this is IE, you have alpha times IE flowing, right? That was the primary parameter of the transistor. So it is natural for it to have some sort of a relationship. If you have a resistor here and a resistor here, the voltage fluctuations here are inducing voltage fluctuation here. So they should be related to each other. So let's look at this. I claim that the total gain of a common emitter in general is negative alpha times the total resistance in the collector to the total resistance in the emitter. If you look at this, you will see it. This is right now, based on this model, the total resistance in the collector, right, is RC. And the total resistance in the emitter is RE, which is explicit, and alpha Rm, which is part of the transistor. So if you want to make a stage that has a gain of close to 5, how would we choose these? I'd make this 5 kilo ohm, and I make this 1 kilo ohm. And you get a gain close to 5. Why it's not going to be exactly 5? Because it's alpha Rm. I mean, if I want to calculate it more accurately, I say, okay, if I bias it at 1 milliamp, it's going to be 25 ohms. So the gain is more accurately 5 kilo ohms divided by 1.025, which is going to be pretty close to 5. And if you want to make it exactly 5, you can make just like play with that resistor or something like that. So the way to design these things is basically saying that the gain of this thing is really essentially a ratio of this to that with this correction. So first order, If you want to make a stage with a gain of 10, you make this 10 kilo ohm and 1 kilo ohm, like 1 kilo ohm and 100 ohms or something like that. If you make it 1 kilo ohm and 100 ohm, if you're, let's say, at the milliamp, then you have to worry about the 25 ohms. Because it's ratio of 500 ohms divided by 125. But that makes it simple. Now, why is that the case? Because it's the same current mostly going through the collector and emitter. Base current is a small current. So the same current flows through this guy and that guy. So whatever fluctuation you see here, it will be reflected here going through that resistor. Now, if this resistor is larger than that, the same current fluctuation will produce a larger voltage. Why is there an alpha here? Because this current is alpha times this current. So instead of thinking about it, so now people sometimes write this in a different way. They write it as negative GMRC divided by 1 plus GMRE. This is the more classic textbook way of writing it. In my opinion, it's an inferior way of writing it. Because it shows nothing. I mean, well, you could make arguments about what it shows. This is the gain without degeneration, and this is the reduction of the gain due to the degeneration. You can think about it that way. This was the original gain without degeneration. This is how much the gain is reduced. And sometimes we write it this way too. Don't take me wrong. We do write it from time to time this way, even if it's necessary. But if you're designing, this is the way you should be thinking about it. So the voltage gain is really the ratio of the total resistance in the collector to the total resistance in the emitter times alpha. And you will see that essentially once you are at a point where this Rm part is small compared to this Rc to Re, the behavior, the primary parameters of the transistor, the exact specific IV characteristic of the transistor becomes irrelevant. As long as you have a device where these two currents are substantially the same or substantially similar, then whatever device you pick, if you put a resistor in the collector, it's in terminal 2 and the resistor is terminal 1. If you have an ATD, then the gain is the ratio of those two resistors. Doesn't matter if it's a MOSFET, a JFET, a vacuum tube, I don't know, whatever, a FunFET, whatever. That's going to be the gain. Okay? So that's an important thing. I mean, it may appear simple, but it's important. Now, of course, what happens to the IV characteristic for the large signal? So as you're doing this, so V in, V out, as you're doing this, what happens is that initially, you again have a similar situation, but the slope as you increase the RE goes up because you are, the absolute slope would go down, really, the absolute value of the slope. It becomes shallower, right? And you may think that, okay, well, is it going to go all the way down? And you know the answer already, right? It doesn't, because at some point, this voltage becomes high enough that this junction, basically these two get close to each other. This device goes into saturation, and beyond that, essentially, this guy will track that because this junction is forward biased. So you have something like this, and then it may come back up if you just use it like this and calculate the V in, V out. Because your input goes up, up, up. At some point, this junction forward biases. This is saturated. From that point on, this voltage will dictate that, because this voltage will always be related to that through a 0.7 volt or whatever the on voltage is. And you did see that in one of the problems that you did. Right? Okay, any questions so far? Yes?
When you're thinking about the impedance at the nodes of the transistor, do you ever find it useful to think about what's physically happening, or do you always think about it in terms of the small signal model?
So that's a great question. So the question is that do we need to really think about it as what's happening physically, or do we think about it as small signal model? See, we want to create abstractions that enable us to deal with more complex circuits. Well, soon we'll be dealing with like circuits with like 30, 40, 50 transistors in them. And it's good to have the abstractions handy in a way that allows you to think about it quickly and have a first pass thing. Like these kind of approximations. So, well, if you want to make something like that, it's the ratio of these things. And we'll see a lot of these as we go. But it's also important to know where these things come from, what are the underlying assumptions behind them, and what's happening physically. Because when things don't work out a certain way, or if you're looking for something that's not normal, something new or novel, a lot of times you can take advantage of that view. So the short answer is that you need to be able to switch it on and off in your head. Sometimes you just say, okay, I'm thinking only about abstractions. I want to make it as simple as possible. I don't want to think about what's happening to every individual electron that's in there, because it becomes intractable. Sometimes you have to go say, okay, now something interesting is happening, or I need something unusual. What's happening really inside? How can I use that? So it's the ability to go up and down these levels of abstraction that enables you to. But to do that, you need to know what these are, what's happening at each one of these levels of abstraction. So that's a good question. It's somewhat of a philosophical question about it, but it's an important one. All right, any other questions? Yes? No.
So in the plot that you drew, the out increases?
Okay, yeah, here. So I didn't get into too much nitty-gritty of this thing, right? So let's talk about that. So as I increase V in, when V in is 0, right, what is V out? V out is at VDD, right, or VCC. As I increase V in, I start drawing current through here, which basically means I start drawing current through here, which would mean that this voltage gets pulled down, because I'm drawing more current out of it and it's just pulling it down. Now, this voltage is going up, this voltage is coming down. So this, what you see here, this red plot, is what that collector voltage is doing. But if you look at the input voltage, which is the base voltage, that voltage is actually going up, right? So that is essentially this voltage. It's going up. It's Vn. So at some point, right? So think about it. There is a diode here, right? This is an NPN transistor, so it basically means that it's like this. There's a PN junction diode. So when this voltage becomes about 0.5 volt higher than that voltage, when the purple becomes about 0.5 volts or 0.6 volts greater than the red, what happens? This junction now is forward biased, right? So this diode is forward biased, which basically means that transistor is saturated. There are two ways to think about that. Let's think about it as a diode. Now, as I increase V in, now this diode is forward biased, so its voltage is going to remain 0.5, 0.6, whatever, right? 0.7. So this voltage is going to track this voltage with a 0.7 volt or 0.6 volt difference. So it's going to be 0.6 volts below that. So this is going to now start tracking it up. So let's keep one of these curves to avoid confusion. Right? So this was going down as exponential. Once this voltage becomes like 0.5 or 0.6 volts, then this guy tracks it, because now the transistor is really not in forward active region anymore. It's in triode. I'm sorry, in saturation. Right? So it just basically keeps going up. Another way to see that is that essentially this voltage is going to be, this voltage is going to be about 0.1 volts above that voltage, above the emitter voltage, right? What is the emitter voltage with respect to the base voltage? If the transistor is on, this is going to be 0.7 below it, roughly, right? Maybe on. I mean, it varies, but not much, because it's a logarithmic. So that voltage is going to be here. This is where it's like 0.7 smaller. So this is going to be 0.1 or 0.2 above that. This makes a good interview question, by the way, to see if somebody knows what's going on in the transistor, or they just like plug in whatever equations they've seen. But anyway, so you get that red behavior. So it's kind of like very bizarre, right? I mean, like initially, but that's what actually happens. And if you look, and this was actually one of the problems you did, right? So this is what's happening with it. Really. Okay. Sure, please.
So this changes from the part where you're doing the grounded emitter, right?
Uh-huh.
What about the resistor changes the curve? Can you explain that?
So, sorry, say again?
So you grounded the emitter,
Uh-huh.
the RE. The curve was like, it ended up saturating and stayed constant at voltage, right? At point.
Right. So basically what happened is that initially we had like something like this, with RE equals 0.
Yeah, so why does that diode argument that you just bring not apply? Can you compare this?
Yeah, well, the diode argument It doesn't apply because what happens is that your emitter, see, this voltage, as it goes, it happens over a short period of time anyway. So it does apply, but when it applies, essentially you're here. You've already made it here. Because for that to happen, it means that this voltage now, if it's ground, if there is no emitter degeneration, right? If this voltage is going up, for this to get below that one, it has to be around 0.5 volts, 0.6 volts below this, right? But at that point means that you've already reached, this voltage has already reached, because this is also 0.7 above this, which means that this is 0.2. So it already has to have reached here. So this happens much quicker. So this is happening, but it's happening before that because now the slope is higher. It has much higher gain. So it does happen. The argument does apply. It just happens by the time it gets down to the bottom. And that's the definition of saturation.
So if you had a really small resistor and the gain was much steeper, then the second curve, the red curve, would also do that or not?
Well, regardless, right? I mean, so you can think about this voltage being around 0.7, 0.8, right? So if this voltage is 0.7, for this to turn on, you need 0.5, which means that this voltage around is going to be 0.2. If there's no resistor here, this is going to happen. Of course, this is a simplified model because there are internal resistors inside the transistor, right? You remember the base had a resistance in series, the collector has a resistance in series, the emitter has a resistance in series. So if you pick some lopsided values, when you're drawing a lot of current, then the voltage drop across those resistors will matter. Because these voltages we are talking about are the voltages across the junction. Whatever ohmic drop you have internal to the transistor due to these parasitic resistances, for example, will add to these. So what appears across the terminal may be larger, partly because of that. And also remember, this is not a hard and fast number, or rule. This is an approximation that comes from the fact that the VBE is VT natural log of IC over IS. So it has a weak dependence on the collector current. Still, it does have a collector current dependence. It's a logarithmic dependence. So for a range of current that you're talking about typically, it may not change that much. And we'll do these numbers more accurately when we talk about biasing and all those things. But yeah. Any other questions? All right. OK, so let's talk about this. Let's continue our discussion. So this is the gain of this common emitter. So, and this, of course, subsumes that. So you say, how does it subsume this case? Well, this is still valid, right? The total resistance in the collector is what? RC. What is the total resistance in the emitter? Alpha RM. Right? Think about T model, alpha RM. So it's RC over RM. So this is generally true. Sometimes write it as GMRC, but you can even write it as RC over RM. So the other question is that how about the input and output resistances of this thing? What is the R in and R out? Let's talk about the R in first. The input resistance. What is the input resistance of this thing? Do you have any feel for what it is? First of all, let me ask you a question. Is it alpha Rm plus Re? It appears that there's an alpha Rm plus Re there, but is that the input resistance? And why not? Yeah, the answer is shaking your head is the correct answer. Why not? Because there's this guy here too. So the key question is, what is this current in terms of IE? What is that current in terms of IE? 1 minus alpha IE, right? Because this is IE, this is alpha IE. So it's the difference of IE and alpha IE, so it's 1 minus alpha IE. Let me just put it a little bit bigger. 1 minus alpha IE. Okay, so that's the current. So what does that tell? So I have an interesting situation. You have this resistor, and the current through this resistor is clearly determined by this voltage. So if you apply a Vx here, let's say V in becomes Vx, right? So if you apply a Vx and you're trying to monitor what Ix is, V in is Vx, therefore IE is going to be simply Vx divided by alpha Rm plus Re. The voltage drop across it. So that's IE. But the current that you experience, Ix, is going to be 1 minus alpha IE. Right? So what is that? So you just multiply by this, you get 1 minus alpha over alpha Rm plus Re times Vx. And therefore, if you calculate Rin, if you do it blindly with equations, with algebra, you get alpha over 1 minus alpha Rm plus Re over 1 minus alpha. Okay, some equation, some algebra. So it's not particularly useful unless we understand what these terms mean. This is, again, a known quantity. That's beta, right? What is this? 1 over 1 minus alpha. Remember, beta was defined as alpha over 1 minus alpha. So if you solve for it, you can see 1 minus alpha is 1 over 1, beta plus 1. Very simple. One equation, one unknown. You can solve. So 1 minus alpha is 1 over beta plus 1. So what do we have here is that you have beta Rm plus 1 or beta plus 1 Re. Now, sometimes you get hung up on betas and beta plus 1s and things of that sort. So unless your calculation is really affected, there are very rare cases where that plus 1 makes a difference in the calculation because something cancels something else and you have the difference of two things. But if it isn't, beta and beta plus 1 are the same thing as far as we are concerned from a design perspective. Because beta is a parameter that's relatively large and it's very inaccurate because it has a sensitive dependence on alpha and assumes that alpha is close to 1. So if alpha is close to 1, it's sensitive to it. So this denominator, you change it, and you literally breathe on it, it changes. You take a transistor, you measure its beta, you just like do this, and then the number changes. Sometimes you look at it, it changes. Right? So I wouldn't get too hung up on this beta plus 1 a lot of times. Shouldn't bother you. If it makes your life easier to make calculations, that's the assumption that you need to make. Because it's built upon layers of assumptions already anyway. So but what is beta Rm? Let's write this thing. Beta Rm is R pi. So it's R pi plus, so this is basically, I would say, R pi roughly times beta Re. So if I want to remember it one way, this is probably not a bad way to remember it. So remember, R pi was the resistance you had in the non-degenerate case. The input resistance, right, was R pi. But now you see something in addition to R pi, which is beta Re. Well, it's really beta plus 1 Re, but yeah. But beta Re. Why do you see some of the so the Re, the emitter resistance, is multiplied by a factor of beta. What has happened? Why does it multiply by a factor of beta, more beta plus 1? Yes? Correct, because the current is really beta plus 1 times smaller, beta times smaller, because it's the emitter current versus the base current, right? That's the ratio of the emitter current to the base current is beta plus 1. So since you have the same voltage applied across here, but the current is beta times smaller, so the resistance appears beta times larger, or beta plus 1 larger. This actually relates to something a little bit more general, which we call the reflection rule. So what is the reflection rule? Reflection rule is a relatively straightforward thing. So what it says is that, and it's easy to see. So let's say you have a situation like this. So you have alpha Rm, you have an Re, you have a resistance in the emitter, and then you want to see, and let's say you have a resistance in the base too. Let's say Rb. So this is alpha IE, this is IE, and this current is obviously 1 minus alpha IE, which is IE over beta plus 1. Right? So now if I apply a Vx here, and let's call this Vx prime, what can I say about the relationship between Vx and Vx prime? I know Vx minus Vx prime is going to be Rb times IE times 1 minus alpha, or equivalently Rb divided by 1 plus beta times IE. So it says that but Vx minus Vx prime is the voltage drop across this resistor, right? This is the voltage across this resistor. So if I want to have the same voltage drop across this resistor, but if I wanted to put it in the emitter, could I do that? I could take this resistor and put it inside add it to the emitter stack, as long as I scale it down by factor 1 plus beta, beta plus 1, or beta roughly, but beta plus 1 more accurately. So it says that the behavior of this circuit doesn't change if I take this RB and put it in the emitter and make it, as long as I scale it down by a factor of 1 plus beta, or beta plus 1. I should write that, beta plus 1 there. Why is beta plus 1 better than 1 plus beta? Because it puts the primary emphasis on the beta, not 1. Right? Okay. All right, so this is alpha IE, and this is IE. So it says that from the perspective of the voltages that you see here and the currents, these two are equivalent. And this is called reflection rule. So it says that if you have a resistor in the base, if you have a resistor in the base, you can reflect it into the emitter. You can bring it into the emitter, and as long as you divide it by beta plus 1. And conversely, if you have stuff in the emitter, you can bring them to the base and multiply it by beta plus 1, which is exactly what we did here. If you look at this, this is 1 over beta plus 1. So what we did, we took alpha Rm plus Re and multiplied them by beta plus 1, and that's what you get. Exactly, that's what you get if you do the algebra. So this is a useful thing. So if you're trying to determine resistances and impedances, it says, look, you don't really need to write all these equations. If you see stuff in the base and you want to look at them from the emitter side, divide them by beta, roughly. Beta plus 1, but beta. And if you have stuff in the emitter and you want to look at them from the base side, multiply them by beta. Beta plus 1, beta. That's a 1 between friends. Okay, so that's what it is. So now you could actually do it this way. You could say, okay, what I have in the base is alpha Rm plus Re times beta plus 1, which would give you exactly that. So regardless, the input impedance is larger than what you had in the case of a non-degenerate case. Right? In the non-degenerate case of when there was no resistance, it's increased by what? So this was the non-degenerate resistance. If you set Re to 0, you will see that it reduces to that resistance. It reduces to R pi. And whatever you put in the emitter gets multiplied by beta. So it makes it what kind of a good kind of a what? Sensor for what? Is it a good current sensor or voltage sensor that has a high impedance? A voltmeter, a good voltmeter or a good ammeter? A voltmeter. It's a good voltmeter. So it becomes better for measuring voltages because it loads it less. Which means that it allows you to maintain the voltage unperturbed depending on what the source resistance is. Okay? How about its output resistance? Well, if I look at this like this, look at it like this, the way it is right now, the output resistance is pretty simple to calculate, right? What is the output resistance? You null all the independent sources, which means that you set this to 0. You set this 0, the voltage across these two resistors is 0. IE will be 0. This current source becomes 0. What is the output resistance? Just RC. But you can see that that's incomplete because we have ignored RO in these calculations. So what if we take RO into account? Let's do that. Let's take the RO into account and see what that gives us. So let's go to the model again. So now this time what we are trying to do, so this is, again, our T model, alpha Rm. And then this time we are putting the RO in there too, RO. And then you have the RC on the top. So let's not worry about that because whatever resistance you will see, and I'll show you what I mean by that, will be in parallel with RC. So let's say this is RE. So we are trying to determine the output resistance here, R out. Do you agree that this R out will be the parallel combination of this resistance, the resistance from this node to ground looking up, and the resistance from this node to ground looking down? And what do you see looking up? RC to ground, right? What do you see looking down? We don't know. We have to find out. How do we find that out? We null the independent sources, which basically means that we ground this node for that calculation. So since we know we are going to get there, let's focus on this for a second. Let's forget about the RC. And we know whatever we get is going to be in parallel with RC. So there's an RC looking up. We'll deal with that later. We are trying to find out what this intrinsic R out of the stage is. Prime. So what is it? Well, we have IE. So this current is IE, and then this is alpha IE. And we are applying a test voltage here. So we will apply a test voltage of Vx, and we want to measure Ix to find out what R out is. Okay, how do we do that? Well, it's relatively straightforward if you look at it carefully. This resistor and this resistor in parallel. Do you see that? These two resistors are in parallel because this end is also grounded. So do you mind if I take this resistor, detach it from here, put it down here? So this is what I'm doing. I'm just putting it down here, connected to ground, alpha Rm. And remember, the current is now going this way. So this is IE because of the direction here. And then this is also ground, so I just keep it simple here. So what we are trying to find out is IE in terms of Vx. So from that, we can calculate Ix. So the first thing we need to do is we need to estimate. So this branch, what is the current through this branch? It's Vx divided by this resistor of this combination of these three resistors, right? So this current we're trying to find out. Now, if you were just doing things blindly, so well, yeah, it's a parallel combination of these two in series with that. We can write it like that. It would become a little bit of a messy equation. You can solve it, and then you can simplify it. Or you can make an observation about the relative sizes of these values. So do you agree that this parallel combination cannot be greater than alpha Rm or Rm? So at the largest it can be is Rm. I mean, it can't even be Rm, but fine. Let's say it's Rm. What is this? RO. What's the typical relative ratio of these two? Large, 10,000, 1,000, depending on what the parameters are. So this is a much larger thing compared to that. So if this is like a 100 kilo ohm, this is going to be 100 ohms or 50 ohms or something like that. So do I need to really worry about the exact value of these things when I'm thinking about finding this value? No. So what I can say is that this current is essentially Vx over RO. Because that's what the dominant part of this total resistance is. It's roughly RO. Because it's RO in series with some small resistor. Okay? Now, that current is divided between these two resistors. So there's a current divider here. So this is Vx over RO with a good approximation. And then I need to calculate IE in terms of that. So how do I divide this current? It's a current divider, right? What's the current divider ratio? It's this resistor divided by the sum of those two resistors. So it's going to be, so this current, IE, is going to be negative Vx over RO times RE divided by RE plus alpha Rm. Everyone agrees? This is just a current divider of whatever this current is, divides depending on the relative sizes of these things. So that's IE. So that's this IE. So that tells me what this current is. So this current is alpha times that. So what is this total current? That's what I'm trying to find out. This is Ix. So Ix, do you agree that it's this current plus this current? Okay, so this current is Vx over RO. And this current is alpha times this thing, which basically becomes negative Vx over RO alpha Re divided by Re plus alpha Rm. And so it basically becomes Vx over RO, 1 minus that, 1 minus alpha Re divided by Re plus alpha Rm. And now this is one of the places that I will not make that approximation because you will see why. I would not drop alphas to be 1, for example, here. because we are calculating the difference of RE and alpha RE. Right? So because you get an RO, so you get 1 minus alpha RE, or let's put it this way. It becomes alpha RM plus 1 minus alpha RE divided by alpha RM plus RE. Now, okay, and from this, if I did, now I have Vx to Ix ratio, right? That's what RO is, R out prime. So R out prime is basically RO times that, alpha RM plus RE divided by alpha RM plus RE times 1 minus alpha. We are going to simplify this a little bit more. I'm going to divide the numerator and denominator by alpha. I should have probably done it here. Yeah, let's do it here first, because so we can keep a clean result up there. All right, so let's do it here. Let's divide them by alpha. So what you get is Vx over RO. You get Rm plus, what do you get? 1 minus alpha over alpha. What is that? What is 1 minus alpha over alpha? 1 over beta, right? So it's Re over beta divided by Rm plus Re over alpha. So that's what we have. So we have Rm plus Re over alpha divided by Rm plus Re over beta, which you can also write, if you multiply both numerator and denominator, by Gm Ro times 1 plus Gm Re over alpha divided by 1 plus Gm Re over beta. Okay. All right, fine. Another equation. Great. What does it mean? Let's see what it means. So, and this is the, remember, this is the intrinsic part. So the total part, R out, was Rc parallel this intrinsic part, right? Which we had dropped already. It was an Rc looking up. We had ignored. Okay, so what does it mean? Let's see how it behaves. So, okay, so let's set up several different scenarios, right? Let's look at 3 different scenarios. The first scenario is when Re is very small. How small? Let's say Re is much smaller than Rm. If Re is much smaller than Rm, what is this value going to reduce to? Well, if Re is much smaller than Rm, then Re divided by beta is also going to be much smaller than Rm. So it becomes basically Rm over Rm times Ro, so it becomes R out is Ro. You can write it this way, but it doesn't matter. Okay? Now, what if Re is greater than Rm, but still much smaller than beta Rm, which is R pi, or R pi. So Re is between Rm and R pi, but it hasn't quite gotten to the R pi yet. So what happens in those scenarios? Well, this term matters now, right? But this term doesn't still. So you get this divided by that, or you can, so basically it becomes Rm plus Re over Rm, which you can write as 1 plus Gm Re. So this is something that you see commonly in a lot of situations, say 1 plus Gm Re. The output resistance is increasing by a factor that's determined by Re and Gm. So now your output resistance, as you increase your Re, as you're increasing your emitter resistance, your output resistance is increasing. And this is important, we'll see why. Now, there's another scenario when Re is even greater than beta Rm, or R pi. If Re is greater than that, then what happens? Then these 2 terms dominate, right? So what do you get? What does this whole thing become?
1 over 1 minus alpha?
Or beta. Roughly, it's beta over alpha, right? Because these 2 terms don't matter. It becomes beta Ro, right? It's beta over alpha Ro, but just like say, roughly beta Ro. And that's the limit, right? If you make Re infinity, It's not going to go above this. So there's a limit it reaches. The output resistance reaches a limit. And you will see, the output resistance is important. Why do we get so hung up on the output resistance and how high it can be? The reason is simple. Because the way to get gain is to have a GM, a drive, and a load resistance. And the only way to increase the gain, really, is to increase one of these two. Either the drive capability or the output resistance. If you can increase the output resistance without compromising other things, that's an easier way to do it. Because increasing the drive capability usually requires other things, like power consumption and things of that sort. So if you have a certain amount of current, you want to get, in several situations, a large output resistance. You remember we said that we are going to be on this quest for gain, right? So that's where we are going to be going with that. So this is beta RO. So that's the maximum output resistance this can have, this stage. And you will see this is actually different when you go to a MOSFET. Yes? Go ahead.
When you're calculating the current through resistor RO,
Here. Yeah.
are we just assuming that RE is a lot smaller than RO?
I was assuming that RM is much smaller than RO. Right? And it usually is, right? Let's say at 1 milliamp, this is 25 ohm, this is, and it's like VA is like 100 volts, it's like 100 kilo ohms to 25 ohms. So it's hundreds of kilo ohms to tens of ohms. So that doesn't matter. It's this tiny resistor in series with a large resistor. It's not going to play a role in determining the current, but it will play a role in determining how the current is divided between this one and that one. Right? Any other questions? All right, so here's the question. Here's the thing. What happens when in MOSFET? What do you think would be different in MOSFET? In a classic MOSFET? What is different in this? Which one of these terms would be different if you look at it? Before we do that explicitly. Well, alpha is what in MOSFET, in the classic MOSFET? 1. So alpha is 1, beta is what? Infinity as a result, right? Because beta is whatever, right? Alpha over 1 minus alpha. So if alpha is 1 and beta is infinity, this term disappears. So you will end up here, right? So there is no limit like this, at least fundamentally, for the output resistance, how much it can be increased. So you increase the RE and you increase the output resistance. And you will see it has topological implications. I mean, I'll tell you one example of it. We haven't seen why, but we will see it. The topological implication is that you see double cascodes. You see triple cascodes in MOSFETs, but you don't see them in bipolars often. Because even if you make your resistance infinity in the emitter, it's not going to go above that. So we'll see that. Just if it didn't make any sense, don't worry about it, because we haven't even told you what cascode is. Okay, so that's one stage. And then we can actually, why don't we do this? Why don't we take a quick break, and then we come back, we'll talk about some of the other stages, and we'll see how they tie together.